Hello and welcome to the CompTIA Cybersecurity Analyst CSA Plus Certification Study Guide. In this video, we will discuss Chapter 1.2 Network Architecture. Please like, subscribe, and hit the notification bell. Network Architectures. There are different network architectures that are also fundamental to IT. These can be divided into their locations and their architectures. Today, many networks are located remotely in the cloud. However, some networks are still located locally on an organization's campus in an on-premises environment. Cloud computing. Different from traditional IT models, a divergent approach for computing has gained widespread use today. This approach is known as cloud computing. Although various definitions of cloud computing have been proposed, the definition from the National Institute of Standards and Technology, or NIST, may be the most comprehensive. Cloud computing is a model for enabling convenient, on-demand network access to a shared pool of configurable computing resources such as networks, servers, storage, applications, and services that can be rapidly provisioned and released with minimal management effort or service provider interaction. Cloud computing is a much more flexible approach to computing resources. Cloud computing allows an almost endless array of servers, software, and network appliances to be quickly and easily configured as needed. And it is a pay-per-use computing model in which customers pay only for the online computing resources they need. As computing needs increase or decrease, cloud computing resources can be quickly scaled up or scaled back. Because cloud resources are available online, users from virtually anywhere around the world can access them through opening a web browser without the need for installing additional software. On-demand self-service. The consumer can make changes such as increasing or decreasing computing resources without requiring any human interaction from the service provider. Universal client support. Virtually any network device, like a desktop, laptop, smartphone, or tablet, can access cloud computing resources. Invisible resource pooling. The physical and virtual computing resources are pooled together to serve multiple simultaneous consumers that are dynamically assigned or reassigned based on the consumer's needs. The customer has little or no control or knowledge of the physical location of the resources. Immediate elasticity. Computing resources can be increased or decreased quickly to meet demands. Metered services fees are based on the computing resources used. There are different types of clouds. A public cloud is one in which the services and infrastructure are offered to all users, with access provided remotely through the internet. Unlike a public cloud that is open to anyone, a community cloud is a cloud that is open only to specific organizations that have common concerns. For example, because of the strict data requirements of the Health Insurance Portability and Accountability Act, HIPAA, a community cloud open only to hospitals may be used. A private cloud is created and maintained on a private network. Although this type offers the highest level of security and control, because the company must purchase and maintain all the software and hardware, it also reduces cost savings. A hybrid cloud is a combination of public and private clouds. On-premises. The introduction of cloud computing has redefined the location of computing resources. Instead of using a centralized model in which equipment and personnel are located locally at an organization's campus, computing now takes place in several different locations, a decentralized model. However, for different reasons, including cybersecurity, not all computing resources have migrated to the cloud. On-premises refers to computing resources that are located on the campus of an organization, on-prem. The different locations of computing resources are listed in Table 1, 2, and illustrated in Figure 1, 7. Table 1, 2 computing locations. Location description example on-premises. Computing resources located on the campus of an organization, on-prem, desktop computer, local area network, data center, off-premises. A computing resource hosted and supported by a third-party remote backup facility FOG. A decentralized computing infrastructure in which data, compute capabilities, storage, and applications are located between the data source and the cloud automated guided vehicles on an industrial shop floor. Edge computing that is performed at or very near to the source of data instead of relying on the cloud or on-prem for processing Internet of Things device. Cloud, a remote facility for computing artificial intelligence processing engine. How much of an enterprise's network architecture should be migrated to the cloud, and how much should remain on-prem? A traditional three-tier on-prem architecture is illustrated in Figure 1. 8. Note that for simplicity, no security appliances are illustrated. This multi-tiered design helps control connections, provide scaling, and increase security. An enterprise could migrate Tier 1, web servers, and Tier 2, application servers to a cloud computing provider but keep Tier 3, database servers on-prem for security. However, it could just as easily migrate all three tiers to the cloud computing provider. Such a decision will need to be based on several different factors. Network architectures include network segmentation and software-defined networking. It would be unthinkable to have an office building in which anyone could freely enter any room or office. Instead, office buildings have different areas with different levels of access. While a lobby is generally an open area for almost anyone to initially enter the building, security guards and technology devices restrict access to other areas, such as only allowing approved personnel to their own offices. And within those areas, there are even more restrictions. A regular employee can enter their office but is restricted from entering the Security Operations Center, SOC, that monitors and manages information security functions. In a similar way, a network infrastructure should be designed like an office building, with some areas available for general access while other parts of the network having successively tighter restrictions. For example, a public-facing web server needs to be in an area in which anyone can access it, while a server with sensitive corporate accounting data must be in a highly restricted area of the network. And the most restricted level of all can be a network that is physically isolated from all other networks or the internet. By creating these security zones of different levels of access, it creates a higher level of security through network design. This is known as network segmentation. Network segmentation can be achieved in two different ways. The first is by physical segmentation, or breaking down a larger computer network into a collection of smaller networks, subnets. A physical network appliance acts as the gateway into the subnet, controlling which traffic comes in and goes out. Physical segmentation is relatively straightforward to administer because the topology is fixed in the architecture. Logical segmentation creates subnets via virtual networks or through network addressing schemes. It is more flexible than physical segmentation because it requires no wiring or physical movement of network appliances to create the subnet, and automated provisioning can simplify the configuration of the smaller networks. Two examples of cybersecurity network segmentation are a jump server and an air gap. Jump server. A jump server, shown in Figure 1.9, is a minimally configured administrator server, either physical or virtual, within a restricted area of the network called a demilitarized zone, DMZ. Running only essential protocols and ports, it connects two dissimilar security zones while providing tightly restricted access between them. An administrator accesses the jump server, which is connected to the administrative interface of the devices within the DMZ. To further limit the vulnerabilities of a jump server, administrators should ensure that all jump server software is regularly updated, limit the programs that can run on it, implement multi-factor authentication for logins, do not allow outbound access or severely restrict access from the jump server, and use access control lists, ACLs, to restrict access to specific authorized users. In recent years, an additional security configuration has been used to limit risks when administering a DMZ. Instead of an administrator connecting to a jump server from just any computer, only a dedicated secure admin workstation, SA, can be used to connect to the jump server. Using a SA prevents an administrator's infected computer from compromising the jump server. In order to keep a crucial network or endpoint from being compromised by infection or data exfiltration, an air gap can be utilized. This solution completely isolates the network or endpoint from all external sources, including any network connection or external ports, like a USB port, into which external media can be attached. This isolation is called an air gap because the devices to be protected have a separation between them and all other devices that only consist of air. Air gaps are often used in environments such as nuclear power plants in which computers and connected systems must be completely isolated from the external world. Air-gapped was not a term that originated with network infrastructure. It has been used for many years in the field of electricity, referring to the space between two objects magnetically related, like the rotor and the stator in a dynamo, or between two objects electrically related, such as the gap between an electrode and the tip of a spark plug. Virtualization has been an essential technology in changing the face of computing over the last decade. Racks of individual physical servers running a single application have been replaced by only a few hardware devices running multiple VMs, simulated software-based emulations of computers. VMs have made cloud computing possible. As computing needs increase or decrease, cloud computing resources on VMs can be quickly scaled up or back. Networks can also be configured into logical groups to create a virtual local area network, VLAN. A VLAN allows scattered users to be logically grouped together, even though they are physically attached to different switches. The computing landscape today would simply not be possible without virtualization. Yet VMs and virtual LANs run into a bottleneck, the physical network. Dating back over 40 years, networks comprised of physical hardware like bridges, switches, and routers have collided with the world of VMs and VLANs. Consider this problem. A network manager needs to make sure the VLAN used by a VM is assigned to the same port on a switch as the physical server that is running the VM. But if the VM needs to be migrated, the manager must reconfigure the VLAN every time that a virtual server is moved. In a large enterprise, whenever a new VM is installed, it can take hours for managers to perform the necessary reconfiguration. In addition, these managers must configure each vendor's equipment separately, tweaking performance and security configurations for each session and application. This process is difficult to do with conventional network switches because the control logic for each switch is bundled together with the switching logic. What is needed is for the flexibility of the virtual world to be applied to the network. This would allow the network manager to add, drop, and change network resources on the fly quickly and dynamically. The solution is software-defined networking, SDN. SDN virtualizes parts of the physical network so that it can be more quickly and easily reconfigured. This is accomplished by separating the control plane from the data plane, as illustrated in Figure 1.10. The control plane consists of one or more SDN servers and performs complex functions such as routing and security checks. It also defines the data flows through the data plane. The goal of an SDN is to allow a network administrator to shape, construct, and manage network resources, such as traffic and bandwidth, from a central console without modifying individual network hardware appliances. In an SDN, the control plane is essentially an application running on a computer that can manage the physical plane. If traffic needs to flow through the network, it first receives permission from the SDN controller, which verifies that the communication is permitted by the network policy of the enterprise. Once approved, the SDN controller computes a route for the flow to take and adds an entry for that flow in each of the switches along the path. Because all the complex networking functions are handled by the SDN controller, the switches simply manage flow tables, whose entries are created by the controller. The communication between the SDN controller and the SDN switches uses a standardized protocol and application programming interface, API. The architecture of SDN is very flexible, using different types of switches from different vendors at different protocol layers. SDN controllers and switches can be implemented for Ethernet switches, Layer 2, Internet routers, Layer 3, transport, Layer 4, switching, or application layer switching and routing. With the decoupling of the control and data planes, SDN enables applications to deal with one abstracted network device without any care for the details of how the device operates. This is because the network applications see only a single API to the controller. This makes it possible to quickly create and deploy new applications to orchestrate network traffic flow to meet specific enterprise requirements for performance or security. From a security perspective, SDNs can provide stronger protection. SDN technology can simplify extending VLANs beyond just the perimeter of a building, which can help secure data. Also, an SDN can ensure that all network traffic is routed through a firewall. And because all network traffic flows through a single point, it can help capture data for network intrusion systems, NIDS, and network prevention systems, NEPS. Both network segmentation and SDN can be utilized in either the cloud or on-premises. If you find this video useful, please hit the like button, leave a comment, and subscribe to the channel. To see more videos like this, please click in the rectangle in the middle of your screen. To see other videos from this channel, please click the circle on the bottom right. Thanks for watching. See you on the next one.